the greatest chemical mysteries of our time.
All right. All right, this is kind of like an icebreaker slide. I like to get people laughing, it makes me less nervous. My palms could fill a bathtub right now with sweat. So anyway, one of my favorite things about being a chemistry major is the questions I get asked when I tell people I'm a chemistry major. A lot of people think chemistry is kind of weird, and they often don't understand it. So these are some questions that chemistry majors are often asked. A couple years ago, this was a common question people were asking: is water wet? You know, kind of just a weird thing that people were talking about. What is an atom? Something that people think I could explain in one sentence, which people have spent their whole lives trying to figure out. Why does nail polish smell so bad? This is a question I have of myself. I hate that smell, and I feel that my fiance likes to paint her nails while I'm in the room just to spite me. Ooh, why do you have lines on your face is a classic question after lab. Because goggles do not do us good justice. This is a classic. Oh, you're a chemistry major? What's number 112 on the periodic table? You know, like, that's what chemistry is memorizing. Although maybe Dr. Cole can tell you. And the final one, my favorite. You tell someone you're a chemistry major and their first thing is, I hate chemistry in high school. Like, what am I supposed to follow up with that? All right, so this leads into kind of what my talk is about. A mystery that I've been trying to discover for a long time is why, come on buddy, why do jelly beans taste the way that they taste? So throughout my talk, I'm going to be talking to you about chemical receptors and the molecular analysis of cell signaling in your taste buds. And so to go along with this, I have a bowl of jelly beans for everybody to take a few of. So take some, pass the bowl around. So before we get into kind of the chemistry, I'm going to give you a little bit of background in jelly beans, because I think it's fun. So today you can go to the store and you can pick up a bag of jelly beans. This right here once says 49 flavors. I'm sure you can find a bag with much more than that. There are a lot of flavors out there. There's even some today with my favorite, you can get dead fish flavored jelly beans. So over the years I've kind of been thinking about, you know, jelly beans are my favorite candy, so I've been thinking, how do they get these flavors into the beans, and how do we taste these flavors so well? Because, I mean, you can eat something like a peach flavored jelly bean, and it tastes a lot more, I would say, it has much more burst of flavor than maybe your average peach would when you eat it. So how do they make jelly beans like this, and where do they really come from in the beginning? So we're going to look at the origins of the jelly bean. All right, so my fans of Chronicles of Narnia out there probably know what this treat is. The Turkish Delight is a pretty old food that has been around for a long time. It's known for its consistency, which is kind of jelly-like. It's kind of like a gummy sort of thing. These are coated in sugar. Sometimes you can get them coated in chocolate, something else. And then here's another thing, the Jordan almond, which, I don't know if I'm familiar, the history of them goes all the way back to ancient Egypt. I'm sure only the nobles could have them, but they would have almonds covered in honey, and they would eat them as a sweet treat. And so one day in probably the 1800s, some genius decided to combine the two, have the hard coating of the Jordan almond, and have the jelly center of the Turkish Delight. So I'm very proud of this. So, here we go. So somebody combine these two. That took me much longer than it should have. So what do we see next? In the 1800s, in the Civil War era, a man named William F. Tract comes about. He makes a little store. He's a confectionery, which is a word to mean he sold candy. He lived in Boston during the Civil War times, as I said. And he is the first person who is credited as selling the first jelly beans. Now, we don't know if he really made the first jelly beans or if he was the one to come up with the idea, but we know that Boston is famous for its beans in several different ways, and this is one of them. So what he did was he took the formula from those two candies I showed you, and he sold the jelly bean. Now these jelly beans were much different than the ones we know today. They were not flavored like anything else. They were just sugar. So if you bit into the jelly bean, it would just taste like your average sugar. But as time went on, the jelly bean expanded, and they learned how to create flavors, and they learned how to cook flavors in the jelly beans that you're all enjoying. They're kind of somewhat of a cultural icon these days in our society because jelly beans are kind of like a signal for Easter and maybe Christmas and maybe other holidays as well. And even one of our own presidents, Ronald Reagan, is known very well for loving jelly beans. So, seeing the big old smile that that's standing there. All right. So, how did we get from seeing just the sugar jelly beans into having ones like sizzling cinnamon or peach, which are the ones that you're eating right now? So that we can see back in the day when Schraub came up with this to sell them, how do we get them to do this? So here we go. Sweet side. All right. So the short answer here on our taste receptors is biochemistry. If you're not interested in biochemistry, I mean, you can lay your head down, take a nap now, and we'll wake you up when we get back to the good stuff. So the long answer here is some pretty detailed pathways with different proteins and a lot of molecules that go into causing your taste receptors to work. All right. So this is the inside of a taste bud. This is a cell that would be inside a taste bud. And the thing that we want to see here is everything you ever taste all depends on sodium, calcium, and potassium. These channels are what dictate everything that you eat. So when you put something on your tongue that has a specific taste to it, that molecule will bind into a certain receptor, and it will therefore channel these channels to open. It will cause a depolarization, which will then cause an axon to receive a signal, and it will cause an action potential, which then allows your brain to sense that, oh, I just ate salt. And that's how the tastes really come about, is that they go through all these channels. And eventually, those get to your brain. So here are the 5 different tastes we have. We have salty, sour, bitter, umami, and sugar, or sweet. So they are all different, and they all have different levels of complexity to them. First up here is salt. Salt and acids or sour things are very similar in their simple way that they work. So inside the cell membrane of all of your taste receptors, they have this sodium channel. Now, like I said, these are the things that really dictate what makes your taste buds work. So just having sodium land onto your cell receptor, it will sense that there's sodium there, it will go through the channel, you'll taste salt. There's nothing more to it. It's very simple. And the same way goes over here with acids or sour things. The hydrogen ions land on your tongue, they travel through the channel, your brain senses that, and you taste the sour things. And then we get a little bit more complicated when we get down here to bitter things. Now, bitter molecules like quinone or caffeine are a lot bigger than sodium and hydrogen, so they need a bit more flexibility, I guess, when they're going through the membrane. So they use these things called GCPRs, which stands for G-coupled protein receptors. Now, these are big old proteins that sit in your membranes, and they snake through 7 times. And what they do is they help molecules get from the outside of the cell to the inside of the cell. And how they do this is, imagine this purple guy right here has 3 little friends. He has an alpha, a beta, and a gamma subparticle. Now what happens is when you get, say, quinone binds to your G-coupled protein receptor, the alpha particle will run over, it will detach, and it will come over here to phospholipase or to adenylyl cyclase, whatever you're eating. And it will bind, and it will tell this to react and create IP3, which is adenosyl 1,4,5 trisphosphate, which then in turn opens calcium channels, which creates that action potential to give your brain a signal that you're tasting something. So when this molecule goes into the G receptor, it will cause all that to cascade, and then at the end, it will allow the molecule to go through and cause that to happen. So down here, the umami flavor, which is like savory or your meat flavor, it works very similarly to what the bitter does with the G-coupled protein receptor and its alpha and beta and gamma subparticles. Sugars work a little bit differently because if you know anything about sugar, you know they give you energy. They create ATP for you. So what happens when your glucose molecule or your sugar lands into the GCPR, it will go to adenylyl cyclase instead of to phospholipase C, which in turn turns ATP into CANP, which is cyclic AMP or cyclic adenomonophosphate, which can be used for energy in the future. All right, so now I'm going to go into a little bit of discussion about molecules and how we can extract flavors from these molecules. All right, so I've got another treat for you. So while I talk about vanillin, I'm going to give everybody, or hopefully, a vanilla jelly bean. So there are not a lot in here. There's a lot more than I figured would show up. So just take one and pass it down, please. If everybody doesn't get it, I'm sure you've had vanilla in the past. You know what it tastes like. So this is a vanilla molecule. It is very simple, and it is a really good example for what I'm going to talk about. So this over here is a vanilla bean. Vanilla beans are mostly grown in Madagascar because the temperature there is good for growing vanilla beans. So basically what you would do if you want to extract this molecule from a vanilla bean is you would take the vanilla bean, you would chop it up into little tiny pieces, you'd put it into some organic liquids, and in a couple hours you would come out with this molecule extracted. Now the issue with getting things out like this molecule, is that you would have several different molecules along with it. So this is something that happens with natural flavors. When you're trying to isolate one specific flavor, you oftentimes get multiple, sometimes even ones you don't want, or some things that might even be toxic. So it's a little bit about vanillin. Now we're going to look at it in the HPLC. So as Bailey said, I'm a big fan of analytical chemistry. It's what I wanted to do with my life after college. So this is a vanillin sample that's run in HPLC. And we can see here that this is probably a natural extract of vanillin because it's got more than one peak. So we see the vanillic acid over here, and down here are probably some sort of benzaldehyde things because they are usually present in the vanilla bean extract, and they kind of give vanilla a little bit of a nutty flavor. So yeah, we can see here that vanillin takes up almost 85% of vanilla extract when it comes in its natural form. That's a lot, and that's why it makes vanillin a very good example when I'm talking about how flavors work, because sometimes when you're trying to extract a flavor, maybe it's only 5% of what you extract. But with vanillin here, it's very easy to just get that good vanilla flavor that you're already eating right now. And that hopefully is delicious. All right, so now I'm going to go into a little bit of discussion on natural and artificial flavors. All right, so this is our old friend vanillin, if you remember him. So I talked a little bit about how natural flavors come about. I'm going to talk a little bit now about how they're regulated while they're being made. So the FDA, the Food and Drug Administration, has a lot of rules when it comes to natural flavors. When you're making a natural flavor, you have to follow certain guidelines and certain steps so that your natural flavor does not become an artificial flavor. Once it hits a certain threshold, it's like super specific. Like you can like chemically modify a natural flavor until it's like 30%, but if you get to like 30.1%, you're done, and it's an artificial flavor. So pretty much when it comes to vanillin, they don't really do a lot of modifications to it. They just get it from the bean and let it go. But there are some natural flavors that they have to tweak a little bit to get it just right. And so here's another example I said about a little bit earlier, is benzaldehyde. I'm using it as an example because it's also very similar to vanillin in structure. As you can see, vanillin just has a couple more little doodads on them. Yeah, so natural flavors are a part of category of molecules called F&F molecules, which stands for food and fragrance. And so in my research, I've been doing a lot on the food part, not so much on the fragrance part, but they work exactly the same on the food part. If you want a natural fragrance, it has to go through the same steps and the same kind of ways to get it to be called a natural flavor, not a synthetic one, because you want to smell natural, not synthetic, right? Yeah, so, and also when it comes to that, a lot of times smell is a big factor when you're eating. Sometimes it's maybe even more than half the reason you want to eat something is because it smells so good. All right, and now I'm going to move on to artificial flavors. Now, if you're going to take anything away from my talk, remember this. All right, so you all remember what vanillin looked like, right? That was the natural vanillin. Here is the artificial vanillin. You might be thinking, what's up with that? It looks exactly the same. That is because artificial flavors are no different from their natural counterparts. When they are made, as soon as this molecule looks like this, it is vanillin. It doesn't matter if you found it on the moon. If it looks like this molecule, it is vanillin and it will stay vanillin. There's a lot of discussion these days about why you shouldn't eat artificial flavors or why they're so bad for you or why this and that. But when it comes down to it, artificial flavors are barely any different from natural flavors, and in fact, sometimes they're even better for you than natural flavors. So also I have benzaldehyde over here, which is exactly the same as its natural counterpart. So there's not a lot of difference there when it comes to it. Now when it comes to making artificial flavors, there is a lot of difference. Instead of extracting it from a natural source, they do a lot of different things. So I'm going to take benzaldehyde here as an example. So what we can see is benzaldehyde looks very similar to this, to vanillin. So say you want to make vanillin and you have a whole bunch of benzaldehyde left over. This is an example, I don't know if they can do this or not. So say you have a whole batch of benzaldehyde that you have just lying around and you want to make vanillin for profit. So what you could do is take your benzaldehyde, artificially transform it into vanillin, and then boom, you just made a whole bunch of vanillin super cheap, and now you can sell it, and it's even in higher quality than a natural vanillin would be. And I'll show you in my next slide that. Which one's better? So we can see the natural extract here. We have 82% vanillin, which is a lot. But then we have a lot of these side products also that are in on it. So you have this vanillic acid, which gives it some flavors over here in the benzaldehyde benzoic acid too. So vanilla is a really good example of something that doesn't really have a downside to having a natural flavor, but sometimes in these compounds, when you're getting a flavor, they will have toxic or dangerous chemicals in with them in high quantities. So you have to be careful with their natural forms. But we can see that this synthetic vanilla is only vanillin. We don't get anything else from here. And so what this also does is when you bite into that jelly bean, you have that good pop, that good juicy flavor of the vanilla. And that is pretty much because it is 100% vanillin throughout that jelly bean. There is nothing else in there stopping it from being vanillin on your taste receptors. There's no competition for your taste buds to go through. So if you remember anything, remember, synthetic flavors aren't bad. If anybody tells you they are, tell them they're wrong. All right, so I would like to acknowledge the faculty here for getting me through college and for teaching me so much. I'd like to thank Dr. King for allowing me to do this topic, which I've been so interested in. I would like to thank the students for being my friends and helping me through everything. And I would like to thank Jelly Belly Corporation for giving me a topic. All right, are there any questions? Yes?
So my favorite jelly bean is the popcorn one.
Butter
And that
popcorn.
seems like, and so that has like a lot of different flavors going on, right? So how do they get the taste of like specifically popcorn, which seems like kind of strange?
Yeah, so it is strange. So a lot of the ones, like I think about the Bean Boozled ones, how do they make a dead fish flavor? You know, like how do they get that? So basically what they do is they analyze the smells or the flavors through HPLC, and they will see what the molecule looks like. And then through the HPLC, they will make a derivative molecule that looks, smells, and tastes kind of like it, but isn't it. So sweaty socks, for example, you're not actually eating a sweaty sock. You're eating a molecule that kind of is like a sweaty sock, but it used to be in a water. So yeah, with the buttered popcorn, they probably put it through an HPLC. What are the flavors in popcorn? What can we take out of that and then pump into the jelly? Dr. Cole.
One of the interesting things about the rules is it can still be listed as a natural sweetener, even if a natural flavor, even if it doesn't come from the typical source.
Yeah.
A classic weird example is natural raspberry flavor that's derived from beaver anal gland.
Yeah.
You know, which we're going to talk
I've read about that one.
That's, yeah, and I have, it's just, there's a one molecule, raspberry ketone that tastes like raspberry. Also occurs in blueberries and other things. But yeah, if you can produce it that way, and the most extreme example, there's a group known as, what is the name of it? It's a company that now has taken the genome from a number of different natural flavor sources, and they extract out the genetic material that will allow you to produce the flavor combinations that you have. And so they can produce, using recombinant DNA technology, they can produce natural flavors because it's still produced by a biological process that's produced totally in a recombinant DNA technique. But by the FDA rules, it's still listed as natural.
You have to label it GMO.
Pardon?
You have to label it GMO.
No, they don't, not flavors.
Yeah, if it's labeled GMO at all, then it can't be a natural flavor.
Yeah.
All right, any other questions? Dr. Sims.
I'm just curious, so you went through the flavor channels and how that worked. So that's going to work with like your nose or not.
Yes.
Why is it that you, then when you plug your nose, your sense of smell, you don't taste as much?
Yeah, so I don't know if you've ever had a cold before. It's harder to taste things when you have a cold because your nose is plugged up. So pretty much when those taste receptors are working, they work however so much. But then the molecules in your nose that cause the same chemical reactions kind of to smell things, they also give you they also kind of trick your brain into tasting. So when you're smelling things, you are tasting with your nose, I would say, the different molecules. So I would say they kind of work 50-50. So when you bite into something, you are both smelling it and tasting it to create your brain to have the reaction. So when you're just tasting, I would say you have maybe even less than 50% of the reaction that you could be having.
So it's the same reaction in your nose?
It's not the same exactly. I think I don't know how similar it is. I didn't really look into fragrance that much.
The ones in your nose are actually, they're the only neurons that come directly from your brain to the outside.
That must make them a lot more
And there have been people who've had accidents where they disconnect and they totally lose their their sense of smell.
All right. Yes?
So with like the taste receptors, why is it that some people can taste like sour things better than others?
Yeah, so a misconception that I will say is that some people think that your tongue tastes flavors different on different parts of your tongue. That's not true. Every taste bud has all the same sensors. What you're saying, why do some people taste more sour than other people? Or?
Yeah, like why can some people just like pop a lemon in their mouth and they're like, yeah, I can taste it. And then some people will taste it and you're like, ugh.
I think it kind of has to do with exposure. Like how people can eat spicy food more than other people. I think it just has to do with over time you create a tolerance to it kind of. I know with spicy food it's not a flavor, it's because it doesn't really have those receptors, it's just your cells like reacting to pain. Yeah, so I think it just really has to do with your cells kind of understanding what those flavors are and getting used to them. Yeah, I don't know exactly the reason, but
There are some differences too in the number of sensors that you have.
Mhm.
And children have more bitter sensors than adults, which is why children are often not happy with things like broccoli and stuff, which has more bitter compounds in it. But the bitter tastes are actually, there's a whole series of bitter taste buds that vary individual to individual to some extent. So that could be the basis of some of that.
Yes.
So why in school do they teach you that you have different like?
Everything you've ever read in an elementary school textbook is completely wrong. Yes, Dr. King.
All right. So I'm thinking about the brain a little bit. So is this all an illusion? Like what?
I would say so.
What we perceive? What this flavor that I'm perceiving? It doesn't taste like hydrogen ions, you know.
No.
Electrical impulses to the brain.
Mhm. Yeah, I mean, I guess when you think about it, you're not really tasting a flavor, you're tasting or your brain is sensing the ion channels opening and closing. Because those different channels, what happens with the sodium ones open, the calcium ones stop, or the potassium ones close. With the bitter ones, your calcium ones open and your potassium ones close. It's all just that difference in electrochemistry that makes you taste different things. And it's not really, and the molecules that give us our different flavors are just kind of like the key that unlocks those to go back and forth. Yes?
Do you think there's a spiritual component to taste?
A spiritual component? I've eaten some good foods. So. Yeah, I mean, I feel like there's a spiritual component to everything. God gave us our bodies for a reason, and I think He gives us our taste receptors for a reason, I think. Yeah, when we eat anything, I mean, we always bless our food, or at least you're supposed to for as a good Christian. I think there's a reason that food tastes good, and I think it's because God wants us to enjoy our lives. Yes?
Yeah, so you had shown a picture, the structures of the zombie and the vanillin.
I can go back. Take me a minute. There we go.
Yeah, so when you compare these two structures, the vanillin has OH and then methoxyl group.
Mm-hmm.
So in terms of the taste of these two compounds, the OH and vanillin, what would you explain? The structure.
Explain in terms of that?
In terms of the structure, so you have the hydroxyl there, you have the methoxyl, which is actually the structure, isn't it? So I'm sure they're two different compounds.
Oh, yeah.
Isn't it? So how would you explain in relationship to the taste?
Yeah, so their relationship to their taste, I mean, benzaldehyde's a nutty flavor. It's what gives almonds its almondy flavor. But vanillin, these substituents, I would say, give it kind of a more creamy flavor than the benzaldehyde has, because there are benzaldehyde components to vanillin. It does taste a little bit nutty. It's a little bit kind of like benzaldehyde, but I think these constituents here give it a bit more of that vanilla flavor. You know, they give it a little bit more smoothness to it than.
So now vanillin, if we were to remove the methyl there, we put the proper euro, would that have an effect in terms of the taste?
The only thing that, I don't know exactly, but I would say it would probably taste more like benzaldehyde if you took that off and it was still a stable and able to eat molecule. Because I don't know if you take that off.
No, you just, like instead of the methyl there, you put the proper, or you put the butyl, where you have the methyl. But it becomes the methoxyl group. It becomes the ethanol.
Yeah.
But you just change the methyl, you replace it with ethyl or proper or butyl.
Yeah, I am not sure at all how that would change the taste of it. I would think that it wouldn't change it very much if you could even taste a difference in it. But
That's interesting.
yeah, I'm not sure. All right.